Welcome to this talk on the paper, a nearly optimal variant of the perceptron algorithm for the uniform distribution on the unit sphere. My name is Marco Schmalhofer and I'm from Goethe University, Frankfurt. Now let's first consider a quick overview on this presentation. First, I will summarize the results of our work in an abstract. After that, I will give you a short introduction to the considered problem, which will also contain previous research results. Then in section 3, we motivate and present our algorithm, whereas in section 4, we give an outline of the proof of our main theory. So the main contribution of our paper is to supplement the simple perceptron algorithm with a variable learning rate eta, such that it epsilon delta learns homogeneous half spaces in a time that is nearly optimal. In particular, our algorithm needs time O of n squared over epsilon times log over 1 over epsilon plus log 1 over delta, and uses number of examples, which is O of n over epsilon times log 1 over epsilon plus log 1 over delta. And the examples are always drawn uniformly from the unit n sphere. It turns out from previous research that these time and sample complexities are nearly optimal up to logarithmic factors. So the setting is the simple PAC setting, which was considered often in literature. So we consider passive learning of origin-centered half spaces, which are represented by some weight vector W. And for simplicity, we always denote the target half space by F star and its normalized weight vector by W star. The learner is given labeled examples, which are pairs, example, label, where the examples are drawn uniformly from the unit n sphere. So the error is also, like in the PAC model, the probability of misclassifying another randomly drawn example. And note that in this setting, the error is also determined by the angle between W star and W, which gives this expression for the error of a hypothesis W. So also commonly used definition is the epsilon delta learner, and this is an algorithm, is an epsilon delta learner if for each dimension, error parameter, and confidence parameter, the algorithm calls a number of examples and outputs a hypothesis which with probability at least 1 minus delta has error at most epsilon. Classical PAC definition, but note that we are restricted to the uniform distribution on the unit sphere in our setting. So let me outline a little bit on previous work on epsilon delta learning of half spaces. So first of all, by the well-known PAC learning results of Blume et al., Ehrenfurcht et al., and Hausler et al., it suffices to find a linear separator consistent with a sufficiently large number of labeled examples, which is not too large. This can be done in polynomial time by standard linear programming techniques. Beside these linear programming approaches, Baum provided a perceptron variant, which needs essentially n squared over epsilon cubed time steps, and thus beating simple linear programming for the uniform distribution on the unit sphere. For small error parameters epsilon, this was improved by Long in 1994 using again linear programming. Finally, in 1999, Servedio provides a simple algorithm which runs in n squared over epsilon squared time steps. This algorithm is even able to handle noise. So the last row in this table concerns our algorithm, which is the fastest for the uniform distribution. In particular, the time complexity of our algorithm improves on each previous in at least some parameter. For example, look at the results of Long of 1994 and fix an epsilon, then there's an additive polynomial in n, which is bigger than ours by a factor of n to the 1.38. Also interesting is that from Long's work from 1995, it follows that our algorithm is essentially optimal in sample and time complexity. So let me continue with the motivation of our algorithm. So the main idea is to supplement the perceptron algorithm with a variable learning rate eta, which is normally a constant. So consider a single perceptron update where we have the updated hypothesis W prime equals the actual hypothesis W plus eta times B times X, where Bx is a counterexample. Then we have a closed form expression for the error of the updated hypothesis. And the central idea is to choose a learning rate eta that minimizes this expression. Okay, so minimizing the error of the updated hypothesis as a function of eta yields a symbolic value for the optimal eta, which is norm of W times d star plus d times the cosine of beta over cosine of beta plus d times d star, where d and d star are the distances from the counterexample to the target hyperplane and the actual hyperplane, and beta is the actual angle between the two hyperplanes. Okay, this would yield a locally optimal learning rate, but obviously this is useless in practice, since d star and beta are unknown to the algorithm. But nevertheless, we can motivate a useful choice of eta. Assume W already has a small error or angle, which is equal up to a factor of pi. Then the cosine of beta is close to 1, and these distances d and d star should be small. So the upper expression is something like norm of W times d star plus d. And since d star and d equal in expectation, we choose 2d to approximate d star plus d. This is hopefully a good choice for a learning rate. And in fact, it is, we will see. Okay, this directly provides our algorithm, which is very simple iterative algorithm. Input is a number of examples to be drawn from the uniform unit sphere. To be drawn uniformly from the unit sphere. The output is a hypothesis vector W, and the algorithm is as follows. As first hypothesis, use the first example, and for each subsequent example, check if it's a counterexample to the actual hypothesis, and if it is, make a perceptron update with this eta proposed in the past section. So we have W prime is W minus 2 times the scalar product of W and X times X. Okay, and by a case distinction, one can see that this is exactly this update rule with the distances. Okay, it's a very simple algorithm, and it has also nice and simple properties which are crucial for the analysis. And the first ones are this proposition here, this small proposition that says each hypothesis of this algorithm has norm of 1, and after each update, the error is decreasing. These are nice properties, especially the monotonicity of the error, and turn out to be crucial for simple analysis. We also conducted experiments for 2 to the 10 dimensions and up to 10 to the 10 examples, running these 4 algorithms, which is the classical perceptron update rule, the average algorithm of Savidio, the adaptive perceptron algorithm constructed by us, and this opt-adaptive perceptron algorithm, which is the hypothetical perceptron algorithm with the locally optimal learning rate. Okay, one can see that the hypothesis error in this double logarithmic plot of perceptron behaves asymptotically like 1 over s to the 1/3, if s is the number of examples. In average, it's a behavior like 1 over s to the 1/2, and in adaptive perceptron, it's something like 1 over s. Also interesting in this plot is that these hypothetical locally optimal adaptive perceptron algorithm does not asymptotically differ much in the behavior of the adaptive perceptron. In particular, it should be a constant factor in which they differ in its error, in their error. So now let's state the main result. The main result is that there is some s, which is about n over epsilon times log 1 over epsilon plus log 1 over delta, which we could choose and get with adaptive perceptron an epsilon delta learner for origin-centered half spaces if the examples are drawn uniformly from the unit sphere. So let us outline a bit of the proof. Consider the kth hypothesis wk and its angle with w star beta k. Then one can bound the expected error of wk with the help of this lemma, and this lemma essentially says that the expected cosine of the angle of the kth hypothesis is exponentially close to 1. So if one has this lemma, by applying Jensen's inequality, one can conclude that the expected error decreases exponentially in the number of updates with some factor of 1 over n in the exponent. So after we have seen 3n ln 2 over epsilon times delta many examples, we expect to have an error of our hypothesis, which is at most epsilon times delta over 2. Now, if we suppose the output hypothesis, wk, has error greater than epsilon, then due to monotonicity, the error has always been greater than epsilon. So if we draw 2k0 over epsilon, many examples, we expect to have at least 2k0 counterexamples in it. And with the Chernoff bound, one can show that the probability of getting less than k0 counterexamples is at most delta half in this case. So overall, if the error of the output hypothesis wk is greater than epsilon, then less than k0 counterexamples were encountered, or the random error of the output hypothesis exceeds its expected value by at least a factor of 2 over delta. And hence, with the union bound and Markov's inequality, one can bound the probability of outputting a hypothesis with an error bigger than epsilon by delta, which proves the claim. So to conclude, we have found a very simple algorithm, which is perceptron supplemented with an adaptive learning rate. And it turns out that this algorithm is nearly optimal for learning homogeneous half spaces against the uniform distribution on the unit sphere. Interestingly, the algorithm has extremely nice properties. It's simple, it's strictly error decreasing, and it's even conservative, which means that it updates its hypothesis only for counterexamples. Thank you.